So let's spend some time talking about rational functions and specifically asymptotes and holes. So here's our generic rational function. It's in blue. And I want to pick out a few characteristics before we dive into asymptotes and holes. Now you'll notice as x gets very, very big, f of x is getting closer to 0, but it never actually touches the x-axis, even if I look at my graph way out to the right. And if I look as x gets very, very small, so going to the left, the function is also getting very, very close to 0, but it's not actually getting there. So this phenomenon, this line that it approaches but never actually touches, we sometimes draw in a dotted line. This is an asymptote. Now, this one's a little easier to see because of this part right here, and it's called a horizontal asymptote. The other one is a little more subtle, but it also sits in here. Now look what happens as we get closer to x being 0. As x gets closer to 0 from both sides, over here, it takes off. Over here, it takes off. So f of x isn't approaching the same thing. The reason is there's another asymptote sitting right here. This one's really easy to see in the equation because in this equation, x can't be 0. It's not in the domain because it is this vertical asymptote. So we can get the vertical asymptote graphically or directly from the equation. So if I change that denominator, now I know that x can't be -1 because -1 is going to make this 0, and I can't divide by 0. That would move this whole thing left 1, and that asymptote would move to the left as well. If this is my rational function, x can't be 2, because 2 would put a 0 on the bottom of that rational, and I can't divide by 0. It would take this whole function and move it to the right. So that one is easier to get from the equation. The horizontal one's a little easier to see from the graph. So let's dive into this horizontal one a little more. We have to think of a rational function as having a numerator and a denominator. The numerator, let's say it has a degree m, denominator has a degree n. Okay, just an arbitrary letter. So down here where it says horizontal asymptote, if my numerator is smaller than my denominator in degree, the horizontal asymptote is automatically y equals 0. And that's what we have going on here. The numerator doesn't have any x's. The bottom has a degree of 1, so the numerator is definitely smaller than the denominator. If we have one where the numerator is bigger, there are no horizontal asymptotes. If the numerator has a bigger degree, so if I have a numerator with a 3rd degree and a denominator with a 2nd degree, there's no horizontal asymptotes. The last possibility for horizontals is if their degrees are the same. Let's say I have a quadratic on the top and a quadratic on the bottom. If I run into that situation, then I need to make a fraction out of the leading coefficients. So whatever that leading coefficient is in the top and the leading coefficient on the bottom, I go y equal, and I put those numbers into a fraction. So algebraically, this takes a little more work than visually. The vertical asymptotes are sometimes easy to see. Algebraically, we set the denominator equal to 0, and we solve. So let's take a look at some examples. I want to do the horizontal asymptotes first for all of these. So I want to go through this process right here that I just explained. So here I have a degree of 1. Here I have a degree of 2. So when I'm comparing these degrees, the top is smaller than the bottom. I have this situation. So the horizontal asymptote for this one is automatically y equals 0. I don't have to do any other calculating. I know it automatically. For this problem here, I have a degree of 2 on top and a degree of 2 on the bottom. When they are the same, I'm supposed to make a fraction out of the leading coefficients. So now my horizontal asymptote is y equals, I'm going to take the 2 from there, I'm going to take the 1 from there, y equals 2 is my horizontal asymptote. On this last one, I have the same situation. I have a squared and a squared. They are the same power. So I take the numbers in front, which are both 1s, make a fraction out of them. There's my horizontal asymptote. So horizontal asymptote is based off of degrees. I'm comparing the degree of the numerator, degree of the denominator. Vertical asymptotes are all based on the denominator. So if I take this example right here, okay, that denominator factors into an x minus 3 and an x plus 2. So when I set that denominator equal to 0, I get x equals 3, set this one equal to 0, x equals negative 2. That's where I would expect to see my vertical asymptotes. And we're going to dive into this a little more on my next example. So let's put this whole process together. We're looking for asymptotes and we're looking for holes, which I haven't talked about yet. I'm going to start with this one right here. Now you'll notice that the numerator and the denominator are the same power. So I automatically know that my horizontal asymptote is y equals, I'm going to put 1 over 1, I get 1. But now I want to dive into those vertical asymptotes again. On that last example, I did some factoring, so I'm going to do that again. This factors into an x minus 3 and an x minus 2 on the bottom. So you would think that x equals 3 and x equals 2 would be your vertical asymptotes. But I'm also going to factor the top. The top factors into an x plus 3 and an x minus 2. Now, if you need some help with factoring, we can certainly do that, but that's how it factors. And you'll notice something. When I look at it in this form, finding the horizontal asymptote is much easier. When I looked at it in factored form, it's a little easier to find the vertical asymptotes. But something interesting happens right here. Since I have an x minus 2 on the top and an x minus 2 on the bottom, those two factors are going to cancel. So when I'm looking for vertical asymptotes, I only have 1. But there's something going on with this minus 2. Whether I look at it in its original form or factored form, I know that I can't plug a 2 in there. It's not in the domain. But that 2 canceled out. So that issue, that problem, that discontinuity in my domain has a different purpose here. X equals 2 is a hole. Now, they're hard to see on a graph, but if you do use Desmos, or even if you use your graphing calculator, and you kind of go along this graph and you go to x equals 2, you're going to see that 2 is undefined because it is a hole. So in all honesty, this thing has moved to the right 1, that's where its asymptote is. It's moved up 3, that's where it, these may have those backwards. It's been moved up 1 to the right 3. And when you look at the two branches of this thing, if you go to 2, where it's at on your graph, there's actually a hole there. That's why this is talking about asymptotes and holes. Holes are the things that cancel out, those discontinuities that cancel. Asymptotes are the ones that we can't cancel out. So let's take a look at another one, a little more complicated one. This has a third power on the top, a third power on the bottom. They are the same. So I'm going to put y equals, and I'm going to make a fraction out of these. Y equals negative 3 halves. That is my horizontal horizontal asymptote. Now to look at my vertical asymptotes, I'm going to do a little bit of factoring. This doesn't factor. It's a cubic. I don't have any way of factoring this particular cubic. I did factor the denominator though. So I'm going to take a look at this and I see this x minus 2 sitting right here. Since I can't cancel that out, that's my vertical asymptote. If it did cancel out, I would call it a whole, but since I didn't have a factor up here that canceled it out, that's my vertical asymptote, that's my horizontal asymptote. Now, if I go back to domain and range, my domain would be all real numbers except x can't be 2. So they kind of work hand in hand. Vertical asymptotes and even wholes aren't in my domain because they're not on the graph. They're either a whole or an asymptote.